So good evening all of you. So please welcome back to this session, the second lecture on this concept of potential flows. So please confirm the audio. Am I audible to you? All clear? Good. So let's continue the session. So this, I told you, this is some extra part of the XC syllabus which I am teaching you actually. So this potential flows is basically the ideal flows, in other words. So we have defined this potential flows as the flows which are incompressible, of course, and irrotational and also inviscid, correct? So I have given you some quick points of this potential flow in the previous lecture, like how to write the complex potential function, all these things. Okay, so this is the continuation of that basic flows what we have seen. In yesterday's session, we have seen three basic flows. In yesterday's class, we have seen about three basic flows: the flow, uniform flow along x direction, uniform flow along the y direction, and uniform flow inclined at some angle to x axis, correct? So we have seen these three flows, and we have seen by putting alpha equal to 0 or alpha equal to pi by 2, we get the first two cases again. Okay, then we have understood how streamlines actually comes into the picture. We have talked about some things like that. Then this is basically the continuation of this basic flows. Like in today's session, we will see some good things again. So this is the plan of today. We will continue our discussion in flow in a sector. So we have seen in yesterday's class, we have seen when u f of z is u into z power n. I've told you that this u into z power n gives you all some special cases actually. Okay, so let us see how they come. Then we will discuss one very important concept of source and sink, and then we'll talk about this vortex flow and one very important concept which is circulation. In concept of circulation, normally when I'm dealing differential flows, differential analysis of fluid systems, I told you that circulation concept I'll deal in potential flows because it can be done in a much easier sense there, and it actually gives you the meaning of circulation there. Okay, so that's why we have kept this concept of circulation at this point of vortex flows. Okay, so before going to these things, let me have a quick revision of what we have talked about in the previous lecture. So all of you please open the first page of your potential flow chapter actually. Okay, so in yesterday's session, we have started by the conversion systems. Means basically, if you have a velocity vector is equal to ui plus vj, where u and v are the x and y component velocities, of course. So when these are x and y component velocities, then we converted these are in scalar coordinate systems, means in the xy coordinate system. Okay, x component of velocity is u and y component of velocity is v. Now we converted this Cartesian system components into polar coordinates by some equations. Actually, we have seen how those equations came. So we converted these equations using this matrix system: u r radial velocity, u theta azimuthal velocity, times cos theta minus sin theta, and sin theta cos theta. Okay, so this is what we have. So upon expanding, you can write these equations as u is equal to u r cos theta minus u theta sin theta. Okay, and we have also seen this v, y component of velocity, is equal to u r sin theta plus u theta cos theta, correct? So we talked about these things actually. Okay, now when we talked about these things, then we have introduced, so once we establish these things, then we have quick revision of velocity potential functions and also the stream functions. Okay, so we talked about one very important thing, which is the complex potential function. So normally if you take any complex number, z is equal to x plus iy in a two-dimensional plane, where this represents x and this represents the y, of course. So f of z is basically this function, velocity potential function, plus I times of stream function, psi of x comma y. Okay, since the flow is irrotational, always there exists some scalar potential function, which is of course in our case velocity potential function. Okay, and we have seen that this phi and psi individually, and this function f of z, this function f of z, whatever the complex potential function you have taken, we assume that this function is analytic function, means it is differentiable at everywhere. Okay, analytic function, so that there are some properties between phi and psi which are actually satisfied. So in this case, both this phi and psi, they obey the Ch-Mn equations. So CR equations, we have seen CR equations, because there is some bit of mathematical involvement here, so I am just revising the things. Okay, so that you will get in touch with the things that we discussed already. So in CR equations, we have seen in Cartesian, we have seen dou phi by dou x is equal to dou psi by dou y, and dou phi by dou y is equal to minus dou psi by dou x, correct? So we have got this. And in polar form, we have seen dou phi by dou r is equal to 1 by r times of dou psi by dou theta, and dou phi by dou theta is equal to minus r times of dou psi by dou r. This is in polar form. Okay, so we have seen, and we know that individually they both satisfy the Laplace equation. Means del square phi is equal to 0, at the same time del square psi is also 0. Then in yesterday's class we have introduced one very great method, which is the Milne-Thomson method actually. Correct? So we talked about the Milne-Thomson method. So this Milne-Thomson method helps you out in finding the complex potential functions if phi or psi is known to you. Okay, and we know that the differentiation means basically whenever f of z is phi of x comma y plus I times of psi of x comma y, f dash of z is actually equal to x component velocity minus I times of v component velocity and magnitude of this f dash of z, because this is a complex number. So if you calculate the magnitude, you will get square root of u square plus v square, which is nothing but this magnitude of this velocity. Okay, so that we know. And also we have seen in polar coordinates this same expression will be equal to ur minus u I times of u theta into e power minus I theta. So this is also we have seen, I have shown you by using the these equations, okay, these two equations, how to convert this expression into this particular expression. So we have dealt with some, I gave you some basics of complex numbers in the beginning. So these are the main things that we talked about. Okay, then we came across this thing that we talked about some basic flows. Okay, so once we have that understanding, then we started looking at some basic flows. So in the first case we talked about uniform flow along x direction. Uniform flow along x direction. Okay, so for this we have the complex potential function f of z is equal to u into z, where u is the free stream velocity, means basically the velocity at which the flow is actually moving. Okay, so it's a uniform velocity, so u is uniform velocity. Similarly, we have also seen uniform flow along y direction. So this is given to you by f of z is equal to minus I times of uz. Correct? We have minus I times of uz. Correct? These things we have derived actually. Once you know f dash of z is equal to u minus iv, we know what is x component velocity and what is y component velocity. Then upon integration you will get this value. Okay, and also we have seen uniform flow inclined at alpha to x axis. Inclined at alpha to x axis. Okay, so this gives you f of z is equal to u times of e power minus I alpha times z. Correct? So this is what you have. So when you put alpha equal to 0, this value is 0, so I into 0 is 0, e power 0 is 1. This becomes uz, because whenever the alpha angle is 0, then the flow becomes parallel to x axis, so flow along the x direction. Okay, similarly if you put alpha equal to pi by 2, this value becomes minus I. So therefore when you put alpha equal to pi by 2, sorry, this value becomes I, and this function minus I, and this function becomes minus I times of uz. Correct? You all know this, right? E power minus I alpha can be written as cos alpha, cos of minus alpha, plus I times of minus sin minus alpha, plus I times of sin minus alpha, and this is cos of minus alpha is cos alpha, plus I times of sin of minus alpha is minus sin alpha. So this turns out to be cos alpha plus I times of minus sin alpha. So when you put alpha equal to pi by 2, when you put alpha equal to pi by 2 here, this cos pi by 2 is 0, this sin pi by 2 is 1, so you have minus I. So this value becomes minus I, and this becomes minus I u z, which is this particular case. Clear? So that's how this is general condition for any alpha basically. Okay, so we have talked about these things, and also we have discussed about one more flow, that flow in a sector. Flow in a sector. Sector means basically some inclined or some angular diversion for the fluid. So flow in a sector. So for this I have given you this value with f of z is equal to u times of z power n actually here. Okay, so we have given this particular expression. So these are the things that we discussed in the class, and when in this case when n is equal to 1, you have again seen this case gives you the case of the first case. We have plotted the streamlines, equipotential lines. We have seen that streamlines and equipotential lines, they start getting perpendicular to each other. We have seen all these things geometrically. Okay, so these are the things that we discussed in the previous session of basic this potential flows. Okay, so if you are clear till this point, then we will move ahead. Okay, because there is some bit of mathematical involvement here, so I have just revised the things and equations. So is this clear to all of you? So please type in the chat box if this is clear, then we will move ahead. So now let us see this flow in a sector. So the complex potential function, yesterday I have given you that f of z per flow in a sector. If you see, we know that the complex potential function is given by u into z power n is what I have given you. Okay, and now if you see, we have converted this into polar, and we have done some analysis basically. So if you see, we have done this. F of z is equal to u into r e power I theta. I told you any complex number z in a plane can be written as r into e power I theta whole power n. Okay, so now if you differentiate this with us, so this is basically equal to u r power n into e power I theta whole power n. So that can be written as e power I times of n theta. So if you differentiate this with respect to r, we have seen f dash of z into e power I theta. Correct? In yesterday's case, I have shown you dou z by dou r. If you differentiate this quantity with respect to r partially, we'll get e power I theta. So that's why we have e power I theta. So when you partially differentiate, u into n into r power n minus 1 into e power I times of n theta. Correct? This is what you have. So this, if you expand, f dash of z is equal to this e power I theta. If it goes to the other side, then this, if you expand, we have u n r power n minus 1 into cos n theta minus I times of, actually this is plus I times of sin n theta, but let us take minus u n r power n minus 1 sin n theta to this whole power e power minus I theta. Okay, now this is of the form u r minus u I times of u theta into e power minus I theta. Correct? So we identified this thing, that the radial velocity u r is equal to u n r power n minus 1 into cos n theta, and the theta component of velocity is equal to u times of minus, sorry, there is a minus sign also, minus u n r power n minus 1 sin n theta. Correct? So this is radial and theta components of velocity. So we have seen different cases, like in yesterday's case, we have seen for n equal to 1, we have kept n equal to 1, then this expression is turned out to be u and minus u actually here, then we have plotted them. Okay, so when you plot them, again we got the first case, basic flows along the x direction. Correct? Now why this is called flow in sector, let us try to understand now. Okay, so see carefully here. First thing you have is, for example, for n is equal to 2, let us suppose if you write, for example, n is equal to 2. Okay, n is equal to 2. Now tell me one thing, if this u theta is basically 0, okay, so for example in this case, if u theta is 0, then sin n theta should be 0 actually. Correct? So sin n theta is actually 0 in this case. Okay, means if you take the stream function, for example, from this expression, if you expand this, okay, why I am taking only sin n theta 0, you will understand now. See here, this is f of z. Correct? So this is f of z. Now if you expand this, for example, u r power n cos n theta plus I times of u r power n sin n theta. Correct? This is what you have. Yes or no? Now if you see this value, this is potential function in terms of r comma theta, and this is stream function in terms of r comma theta. We know this. Okay, now if you try to observe, okay, we'll see n equal to 2 what happens later, but right now I want to make you understand one thing. Normally if you see, there cannot be any flow across the streamlines. Correct? But if you have stream function, for example, if there is stream function, then you know u is equal to dou phi by dou x, dou psi by dou x, dou psi by dou y, and v is equal to minus dou psi by dou x. Similarly in polar coordinates also you will write some expressions for radial velocity and theta velocity. Okay, theta velocity in the azimuthal direction. Now please tell me one thing, let us suppose if this value of psi is equal to 0, then definitely this u is 0 and v is also 0. Yes or no? Correct? or in general, if you psi is 0, then ur is 0 and u theta is also 0 actually. Yes, please type in the chat box. Let us suppose if I take the value of stream function as 0, because psi equal to c1, psi equal to c2, you have a lot of streamlines actually in a flow. But at one particular streamline, let us suppose if the value of the stream function is 0, then in such case there won't be any flow across that streamline, correct? Because if psi is equal to 0, the partial derivatives of with respect to psi, with respect to r, with respect to theta, all these things will be zeros. So there is no velocity of the flow actually. Means at that location the flow is in static condition. Means basically there is no flow, fluid is in static condition. Now if you see, for psi is equal to 0, psi is equal to 0 actually. So for psi is equal to 0, this implies, what is psi actually? U r power n into sine n theta is equal to 0, correct? This is what you have. U into this r power n into sine n theta is equal to 0. Now from this equation you can easily understand one thing. This u is not 0, because if this u is 0, this function itself does not exist. Okay. Similarly this r is also not 0, because if r is 0, similarly that function does not exist. So this implies sine n theta should be 0 actually. So this implies n theta is either 0 or n theta is equal to pi generally. Okay, because it's a we are talking about the positive plane. So theta is equal to 0 or theta is equal to pi by n. So under these two cases there won't be any flow across the streamline. Okay, now if you plot this, for example, if psi is equal to 0, you can write, if psi is equal to 0, if for psi is equal to 0, magnitude of velocity vector is also 0, correct? So this is the expression of psi is equal to 0. Now if you take for n equal to 2, for example, for n is equal to 2, let us take, for n is equal to 2, if you write the expressions ur is equal to, if you put n equal to 2 here, then 2 u r cos 2 theta. So 2 u r cos 2 theta and u theta is equal to minus 2 u r sin 2 theta, correct? So this is what we have. But if you see, for example, if you try to plot, let us suppose this is the origin, for example, this is the origin. Now if you plot theta equal to 0, theta equal to 0, curve comes like this, correct? So this is how theta is equal to 0 looks like. Similarly, so this is theta equal to 0 and theta is equal to pi by 2. For example, if you take theta equal to pi by 2, the curve appears like this. So this is theta is equal to pi by 2. Okay, so theta is equal to pi by 2 actually here. So theta is equal to pi by 2. Now if this is one streamline, for example, if you take this as one streamline, then there cannot be any flow across this streamline. Means practically fluid is not moving along this layer. Then in such case I can take this as some solid surface, for example. Okay, and coming to stream functions, whenever this n is equal to 0, for example, if you see u r sin theta, sin 2 theta is there actually for you. Okay, now if you try to plot the streamlines, psi of r comma theta is equal to, when you put n is equal to 2 in this, when you put n is equal to 2 in this equation, u r power u r square into sin 2 theta. Okay, so u r square into sin 2 theta. So this is actually some constant value, yes or no? Because if you want to plot streamline, then along a streamline psi is some constant value. So let us take this is some constant, for example. Now if you want to understand this in a Cartesian system, what does this curve actually represents, you can easily understand. See here, this can be written as u into sin 2 theta can be written as 2 sin theta cos theta, correct? So if you write that small r into sin theta into one more small r into cos theta into 2 is also there. So let us write that 2 here, for example. When you expand this, we have 2 sin theta cos theta. I have split this r square into smaller and smaller again. Okay, so y is minus sin, sir, where u theta, in u theta y is minus sin, sir. No, this is not velocities. Okay, I'm just plotting these two, that's it. I'm just plotting theta equal to 0 line and theta equal to pi by 2 line, that's it. Velocity is negative. Okay, velocity is actually negative, but the direction, means if you see this line theta equal to pi by 2 is not negative. Okay, since here there is a minus sign, I have kept this direction bottom. That's why I'm taking this as one streamline where psi is equal to 0 actually. Clear? This minus sign is due to this downward arrow, or this downward arrow is basically due to this minus sign. So that's why I have taken this as one streamline where the fluid is in static condition. There is no velocity. Okay, so that's why it is physically acting as some solid. Okay, so flow cannot cross this streamline, so that's why we can take that as some solid surface, for example. Okay, now if you see, this is equal to constant. Now, so 2u is constant actually, so 2u is also constant. Now in polar coordinates, you know, x is equal to r cos theta, y is equal to r sin theta, and 2u is actually some constant. So this curve in Cartesian system, this represents xy is equal to constant actually. Okay, so xy is equal to constant is what you get in terms of xy coordinate system. So here if you plot these curves on this polar graph, look, either in Cartesian system or polar system, only the equations change, but the shape of the curves doesn't change, correct? Like for example, if I want to draw a cycle in Cartesian system, I write this equation as, if for example this radius is 1 unit, x square plus y square equal to 1. Okay, in polar coordinates I write r is equal to 1. That's it. Okay, the modulus of r is equal to 1 actually. Okay, mod z is equal to 1. Mod z is equal to 1 is what we write. Okay, so both equations are different in complex numbers, means in polar coordinates if I write, then these two equations are different, but and if I write z is equal to r into e power I theta, anyhow magnitude of e power I theta is 1, so modulus of r is equal to 1. So this equation also represents the same cycle. So equations are different, but the shape of the curve and the location of the curve remain same. Okay, so therefore this equation and this equation are same. Therefore if you see this equations xy is equal to 1, xy equal to constant, they represent rectangular hyperbolas. You know, normally we'll call this process as hyperbolic process. Normally if you take isothermal process, for example, for ideal gas, of course, at time t equal to constant, pv equal to constant. Okay, so when you plot pressure versus volume axis, you get rectangular hyperbolas, correct? Similarly here, when xy is equal to constant, these are set of rectangular hyperbolas. Okay, so whenever they are rectangular hyperbolas, then definitely you can draw the streamlines in this way, that so this is, for example, psi is equal to 1, this is psi is equal to 2. Okay, so rectangular hyperbolas, psi equal to 3, psi equal to 4, like this. Okay, so you have lot of rectangular hyperbolas actually at this location. Maybe this is some psi equal to 4, psi equal to 3, psi equal to 1, all these things. Okay, so the streamlines in this case are rectangular hyperbolas. So whenever they are rectangular hyperbolas, you can assume there is some flow which is happening in this direction. So there is some basically some wall kind of thing, or some sector in which there is some flow. Okay, so that's why when n equal to 2, this is the case, and these are the streamline equations. Okay, so the streamline equations are of this form. Clear? Did you understand how we got the streamlines xy equal to constant? So the streamlines are actually rectangular hyperbolas. So that's how we can assume that there is some flow like this happening in one solid bend actually. Okay, since there is no flow across this line, because here whenever you put theta equal to pi by 2 or theta equal to 0, this expression goes to, means the stream function value goes to 0. So that's why we have this value. Okay, now if you see, for example, for n equal to 3, let us say for n equal to 3, for n is equal to 3 actually. Okay, when you put n equal to 3, then this implies for psi is equal to 0, for the stream function value to be 0 totally, for the stream function value to be 0 actually, what comes here is tell me what comes here. If this theta is equal to 0 or theta equal to pi by 3, in place of n you are keeping 3 now, so theta equal to 0 and theta equal to pi by 3, theta is equal to pi by 3 actually here. Okay, now if you, for example, again, if this is origin in the system, if this is origin, then theta equal to 0 is this, theta equal to 0 is this here, and theta equal to pi by 3 is something like this. Okay, so theta equal to pi by 3. So let us suppose this is the streamline along which psi is equal to 0. Okay, so this is the streamline in the flow where psi is equal to 0. So then this is some 60 degrees, pi by 3 means 60 degrees. Okay, similarly if you put n equal to 4, then 45 degrees sector. When you put n equal to 6, 30 degrees sector. So like this equation z power n will actually give you the case of flow in a sector. Are you physically understanding why this is called flow in a sector? Because along this streamline there cannot be any flow and there is no movement of fluid along this particular streamline. So practically we are assuming that stationary line of fluid as one solid surface, because practically fluid cannot enter this. Okay, fluid cannot cut the streamlines, so there cannot be any flow across this line. So even though there is only liquid in actual condition, we are assuming that there is some solid surface, because practically flow cannot enter this. Okay, that's why this is called flow in a sector. This situation is ideal to flow in a sector. Clear? Fine. Now let us see. In this case, if you try to draw the stream line, basically stream functions, psi of r comma theta is equal to, when you put n equal to 3 in these equations, when you put n equal to 3 in this equation, u r cube into sine 3 theta. Okay, so u r cube into sine 3 theta actually. Okay, so this is what we have, u r cube into sine 3 theta. So in this case we can actually write, look, I'll tell you one thing. In this case what happens is, if you plot that equation, if you put x, if you expand this sine 3 theta, and if you put x equal to r cos theta, y equal to r sin theta, these terms, you will get the curve something like this. This is how you will get the flow. Means the streamlines in this case are obtained along this particular line. Okay, so this is for example psi equal to 1, psi equal to 2, psi equal to 3, like this. Okay, so the flow, actually the streamlines look in this fashion. I cannot mathematically show you because it will be slightly lengthy, but I'll show you graphically. I'll take the advantage of Google and I'll show you polar curve plotter, for example. Okay, polar graph plot. Okay, fine. Okay, so graphs of polar equations. No, let us take one software to plot this polar curves. Okay, so let us plot this. Yeah, we got the equation. So let us see how we'll plot this. Look, along a streamline this value is constant, correct? So along a streamline psi is equal to constant. I just want to show you why this shape of line comes out. Okay, so along a streamline psi is equal to constant. Okay, psi equal to constant. Now let us suppose, for example, if you take psi is equal to 1, this is constant along the streamline, and u is also 1, for example, then in that case we have 1 is equal to, you can take anything, basically some constant is what I mean, r cube into sine 3 theta. Okay, so this implies r is equal to 1 by sine 3 theta whole power 1 by 3. Correct? So this is the function. So r of theta is given by this value. Look, it need not be 1. For example, if u is 10 and this stream function value is 3 along a streamline, then 3 by 10 can be 0.3. It can be anything. My main intention is this is some constant actually. Okay, this is some constant. So here, just to make you understand, I am taking the value of that constant as 1. Okay, now if you plot this equation, I will show you how it comes out. So if you see, then this is cube root of 1 by sine 3 theta, correct? So 1 by sine 3 theta. So if you see, first of all, 1 by sine 3 theta. Where is theta? Here. Okay, so 1 by sine 3 theta. So whole power. Okay, so power, I think just a minute. 1 by sine 3 theta whole power. This bracket can be taken off, then this bracket can be taken off because I just want to show you. Okay, 1 by 1 divided by, or 1 by, let us write directly, division. Okay, here it is division. So 1, let us write this. So division of 1. Okay, I think I have typed modulus, just a minute. So division here. So 1, and here it is sine 3 theta. Where is theta? Sine 3 theta. This power 1 by 3. Okay, so power 1 by 3. Let us write power 1 by 3. So 1 by 3. Okay, so if you plot this for example, so if you anyhow that is there, so 1 by 3. So if you plot this, let us see, I will show you the shape of the graph actually. Okay, so if you see, you can see the curve actually, of course we are talking only in the first quadrant. So if this point is origin 1 2 3 4 5 6 and so on, 1 2 3 4 5 6 and so on, you see the curve, the plot of that curve, which curve, this 1 by sine 3 theta whole power 1 by 3. So that curve comes something like this. Okay, so it is the equation actually comes out and bends like this. Okay, so that's what the same shape we have actually drawn here. Clear? Understood? Because practically if I try to expand this as 3 sine theta minus 4 sine cube theta, all these things, you will feel little hectic in mathematics, and that's not required also at the moment. But since there is some tool with us, if you plot, then this is how the curve comes, and this is how we have drawn the streamline actually. Clear? So intentionally I have drawn them close to this particular value. So the flow happens in this sector in this direction. Clear? So the flow, if it's traveling along this direction, then because of this bend or something, then the flow actually diverts like this. Clear? Did you understand this? I just want to show you this graph, that's it. Okay, clear? So anyhow, that's the case. So this is how the streamlines actually look in this particular case here. Okay, so psi equal to 1, psi equal to 2, psi equal to 3, and this is anyhow psi is equal to 0 is the curve which is here. And so at theta is equal to pi by 3 and all, we can see theta is equal to pi by 3, the stream function goes to 0. Okay, so stream function actually goes to 0 in that case. Clear? Now we'll talk about 2 more cases, because this is, so that's how, did you all understand, like n equal to 2, n equal to 3, all these things, n equal to 4 5 6, whatever you take, all these things they give you flow in a sectors. Basically sector means basically like some part of a complete cycle, so some bend with some angle. So in such sectors the flow can be idealized by using this equations, u into z power n, using that particular complex potential function for n equal to 2, n equal to 3, all these values you can actually plot this. Clear? Now did you understand physically why these are called flow in a sector? Is this clear to you? Okay, now let us see one more case, 2 interesting cases actually. For n is equal to minus half, actually this is one very good case actually, for n is equal to minus half. When you put n equal to minus half, your stream function value turns out to be something like psi of r comma theta. What is the expression for psi of r comma theta? This expression, u r power n sin n theta, or basically if you put n equal to minus half, theta equal to 0, and theta is equal to, look, theta is equal to, psi is equal to, first of all let us write, psi is equal to u r power minus half into sin minus theta by 2, correct? U r power minus half into sin minus theta by 2 actually here. So this is the stream function. Okay, so therefore the values of theta at which psi is equal to 0, at which psi is equal to 0 are, so at which psi is equal to 0, so here if you put theta equal to 0 is 0 anyhow, when you put n equal to minus half, this becomes minus 2 pi, yes or no, correct? So theta equal to 0 and theta is equal to minus 2 pi actually. So in this case, if you try to observe, you will see one good thing actually. This is origin as usual. Theta equal to 0 is this. Theta is equal to this value is this. Now this is theta equal to 0, of course. Please tell me, theta equal to minus 2 pi means normally you will measure the angles in clockwise, but this is minus 2 pi. So let us suppose if this is theta equal to 0, if you measure in anti-clockwise and if you come back to 2 pi, then can I say theta equal to minus 2 pi is also the same equation like this? Yes or no? This is basically theta is equal to minus 2 pi. Can I say this? Yes or no? Theta is equal to minus 2 pi is also the same equation. Can I say this? Yes or no? So this is how the streamline or the stream function along which theta is equal to, psi is equal to 0 actually. Correct? Now if you try to plot the streamlines actually, now if you see the streamlines in this case, like how we have seen in this case, along a streamline psi is equal to constant. Along a streamline psi is equal to constant, of course. Okay, so here if you actually plot the streamlines, the streamlines come something like this. Okay, so the streamlines, they come something like this. Origin, for example, then in that case, this is how the streamlines actually comes. Okay, so here if you see, this is how the streamlines comes, because this is for the positive and negative values of theta here when you put. So this is how the streamlines actually comes out. Okay, in means if you take all over the plane. Okay, so whenever this is the case, we can assume this situation as there is, and this is having psi is equal to some c1, psi equal to c2, psi equal to c3, all these things. Now what we do is, since the flow is actually happening in this particular direction, we can assume this situation as, let us suppose there is some flat plate, for example, or sharp edge. Okay, so let us suppose there is some sharp edge here, because this axis is very it's like a thin plate which is present. Okay, so whenever there is a sharp edge, and let us suppose if the fluid is coming, then the fluid actually after hitting the sharp edge, it gets deviated like this. Okay, so that's what we will take here. We are not taking any viscosity into the picture, it's only a ideal fluid. So whenever the fluid comes and hit the flat plate, then it actually gets diverted in this particular fashion. So this is how we get the streamlines, and this case of n equal to minus half can be approximated or can be understood as flow past a sharp edge. Flow past a sharp edge actually here. Flow past a sharp edge. Okay, so now I'll show you how this shape is actually coming here. Okay, for example, if you take this stream function is 1, okay, along a streamline psi equal to constant. So let us suppose if you take psi value is equal to, let psi is equal to, for example, 1. Okay, and u is also, for example, 1, let us take. Okay, for easiness in the calculation, then this implies 1 is equal to 1 into r power 1 by 2, which is 1 by square root of r actually. Okay, r power minus 1 by 2 is 1 by square root of r into sine minus theta by 2. Okay, so this is what we have. So this implies r is equal to square root of r is equal to sine of minus theta by 2. So this minus can be taken out. When you do square, r becomes sine square theta by 2. Correct, because this minus sine theta by 2 is there. When you square this value, that minus sign will go out. So this is how we'll get the plot actually. So if you plot this, then this is how we get the shape. I'll show you. R is equal to sine square theta by 2. For example, let me plot the same thing here. R is equal to sine square theta by 2. Okay, so sine, okay, so sine square theta by 2, actually here. Okay, so if you plot r is equal to sine square theta by 2, then here if you see, normally in this case, for example, if you see, the flow happens in this particular case. After some time they again meet, of course, but here if you see, we have taken this psi value is equal to 1. If you take psi equal to 2, some different function again comes out. Okay, so but normally I just want to show you the shape. So the shape that actually happens is this flow. So we take the situation like whenever the flow comes out, and if it hits, then we actually get the shape in this particular fashion. Clear? So that's how I have drawn this particular shape of the streamlines in this particular directions. Okay, so flow comes, hit the sharp edge, and it gets diverted in both the edge, sides of the plate. Okay, so that's how this n equal to minus half can be approximated as the case of flow past a sharp edge. So whenever there is a sharp edge like this, the flow comes out and it gets separated because of the existence of the plate. Clear? Like similarly, for different values of n, you can get different situations. Okay, okay. Now everyone should type in the chat box, guys. Are you all understanding? Because look, I'm not doing any big mathematics. I'm just doing some simple 11th class and trigonometry and some complex numbers. That's it. Nothing big I'm doing actually. Okay, everything is very simple, understandable to you graphically and all. But since the only thing I'm doing now is, since I cannot show you directly if I plot this how I'll get the curves and all, because if I want to show this, I should go to 1 minus cos theta by 2, then I have to multiply r, I have to do different things. Okay, rather than that, I'm using some tools to show you the shape of the objects. That's it. Okay, next I will show you one last case actually, one last case in this flow for n value. You will appreciate that actually. So 5 for n equal to minus 1, for n is equal to minus 1. This is one very powerful case actually, which I'll, okay, let us not deal this right now, because to know this you should know the concepts of source and sink actually. Okay, so let us see. First of all, let us discuss the concepts of source and sink. So source and sink. Okay, so let us discuss these concepts. Then after, when I derive the doublet, okay, that's n equal to -1 situation is called doublet. So when I explain you what is doublet, what is the complex potential function, you will understand that the complex potential function, basically this f of z for doublet is same as the case when n equal to -1. Okay, we will understand that, but to understand that, let us see this here. So concept of source and sink. Okay, so source, like normally in mechanical engineering, this concept of source, normally in electrical also, in terms of charges and all, we'll talk it. So source is basically something which gives continuously, correct? For example, if you're talking about heat engines, then in case of heat engines, we call thermal source as the location from where you continuously get heat energy. Okay, the location is such that even after giving tremendous amount of heat energy, the temperature of the location doesn't change. Okay, so they are called thermal sources. Similarly, in fluid mechanics, this source what we are talking is nothing but the point from where fluid emanates continuously. Emanates means coming out actually. Emanates out continuously in all directions. Okay, so this is source actually, the point from where fluid emanates out continuously in all directions. Okay, so means basically, let us suppose if you have a source here, for example. Okay, so there is some source. So from this point, if you see, fluid comes out in all the directions uniformly. Okay, it comes out in all the directions uniformly. It comes out in all the directions continuously. Okay, so if you see, in this case, the fluid comes out in all the directions continuously. Okay, in all the directions the fluid comes out. Okay, the fluid actually comes out in all the directions. So this is called a source. Okay, so we have a source in this case. So this is source. Now, for a source, what is the complex potential function? Okay, means basically from a point, fluid is continuously coming out in all the directions, in all the 360 degrees, the fluid is actually coming out continuously. So whenever the fluid is coming out continuously, what is the velocity potential function? The complex potential function for this case. Okay, look, I'll ask you something. So try to tell me. We have f dash of z is equal to ur minus I times of u theta into e power minus I theta, correct? This is what we have. Okay, so first of all, I'll give you one hint actually. This f of z in this case is c times log z to the base e is what you get. Okay, so anyhow, we'll see how this is coming, but first of all, this is the idea that I'm giving you. For this kind of source flows, we have c times of log z to the base e actually here. Now try to understand this. So we know this. Now let us suppose if this is a polar coordinate system, for example, can you please tell me ur and u theta values? Ur and u theta values. Look, when you try to write ur and u theta values, one thing that you know is the fluid only moves radially. The fluid particles do not rotate. Means basically, if you take two streamlines like this, so let us suppose if you take two streamlines very close, then fluid can only travel in radial direction. It cannot cut the streamline. So there cannot be any theta direction velocity for the particles. Yes or no? So please type in the chat box. Did you understand this? Whenever the fluid is coming in radial direction, the fluid don't have any chance to go translation in the theta direction. Yes or no? Correct. So please type in the chat box. Can I say this? Because what happens if fluid, let us suppose if there is some particle here, for example, this part, for example, let us suppose there is some particle here. This particle is supposed to move only in the radial direction. This particle cannot cut this streamline and enter. Okay, so that cannot happen. Okay, so now if you see, So the particles can move only in radial direction. So therefore u theta is 0. Next, what about the radial velocity? So please try to understand this. Let us suppose some discharge came out. Okay, now the same discharge should actually travel, yes or no? Means let us suppose if there is some discharge between these two streamlines that's flowing out, at this location also the same discharge should flow out. So for the same amount, because obviously flow cannot enter the streamlines, so discharge between the streamlines is constant, we know this. Okay, so at this location, whenever the gap is very small or the flow area is very small, there is some velocity for this fluid particles. Now when they move to higher radius, the flow area available for the same discharge is increasing, yes or no? The flow area available for the same discharge q is increasing. So in that case, whenever the discharge is remaining same but flow area is increasing, the velocity should actually decrease, correct? So therefore we will take this value as some constant divided by radius, such that as radius increases, this radial velocity decreases. Understood? So did you understand how I have marked ur as c by small r? Yes or no? So please type in the chat box. Is this clear to you? Did you understand these two things here? How ur is equal to c by r and u theta is 0? Because only one thing, here the fluid particles will move at a higher velocity as compared to this location. Because if you see, if these are two streamlines, for example, we'll see how they are the streamlines actually. So these two are actually two streamlines. So whatever is the flow that's entering between these two streamlines, so same flow should remain all over the motion of the fluid, yes or no? Means let us suppose in between these two streamlines, for example, if 1 meter cube of fluid is entering, the same 1 meter cube fluid will also cross this radius, yes or no? We'll go in a step by step way. So see here, if 1 meter cube of fluid is entering this radius, the same 1 meter cube of fluid will also pass this same radius, yes or no? Correct? Yes or no? So please type in the chat box. Yes. Now whenever same amount of discharge is actually crossing, the flow area available between these two streamlines is less as compared to the flow area available at this point, at this higher radius. Okay, so whenever the flow area is increased for the same amount of discharge, obviously velocity of the flow will actually decrease, yes or no? Correct? Clear? Is this understanding clear to all of you? So my intention is to tell you that as radius increases, the velocity of the flow will decrease, because for the same discharge the flow area available is getting higher. Okay, now that's why we have written this ur as some constant which we don't know, but inversely proportional to r, so that as radius increases, this ur actually decreases. Clear? Now I hope it's understandable to all of you. Ashika, clear? So type in the chat box. Is this clear to all of you? Okay, now so if you see, therefore f dash of z is equal to c by r minus I times of 0 into e power minus I theta is what you have. Okay, so this is the function that's available with you. Okay, now if you do the integration, let us see, f dash of z is equal to c by r times of e power minus I theta. Okay, so e power minus I theta. So now if you want integration, then apply Milne-Thomson method. So if you apply Milne-Thomson method that you see in complex calculus, okay, then replace r by z and theta by 0. Correct? So the first variable you replace by z and the second you replace with 0. Like normally in case of Cartesians, you replace x with z and y with 0. Here r with z and theta with 0. So when you do this, this implies f dash of z is equal to c by z into, when you put theta equal to 0, this value is 1, correct? Because when you put this theta 0, e power 0 is 1. Okay, so this is what you have. So this implies f dash of z dz is equal to c by z dz. Now if you integrate this, then we have the complex potential function as c times of 1 by z integration is log z to the base e. So that's how you have the f of z value as c times of log z to the base e. Okay, so this is c times of log z to the base e that I have written. Okay, now in yesterday's class I told you one thing. if you expand this logarithm, for example, then we get this implies f of z is equal to some constant times of log z can be written as half times log x square plus y square plus I times of tan inverse y by x. Correct? So this is what I have told you. That's the reason why I have explained you the logarithm expansion of complex numbers. Okay, so here if you see this f log z can be expanded in this form, half times of log x square plus y square plus I times of tan inverse y by x. Correct? Now if you split this into real and imaginary parts, then definitely this gives you c by 2 times ln x square plus y square plus I times of c into tan inverse y by x is what you have. So therefore this function which is here is your velocity potential function, and this function which is here is your stream function psi of x comma y. Actually here this is stream function. Now if you try to plot this velocity potential functions and stream functions on a 2D graph, see how the curve comes out. So let us suppose this is x axis. Okay, so this is x axis here slightly, and this is y axis. Okay, so this is y axis, origin x y. Now tell me one thing, if you want equipotential lines, along equipotential lines this phi is actually constant, correct? So let us see, along equipotential lines we have phi of x comma y is equal to some arbitrary constant, say c1 for example. So this implies, now this phi of x comma y is equal to means c by 2 times of ln x square plus y square. So c by 2 times of ln x square plus y square is equal to some arbitrary constant. So can I do one thing, if I multiply this 2 and if I divide with c, still this is some arbitrary constant, yes or no? Means if you see 2 I am multiplying here and c I am dividing here, so 2 c1 by c will still be some arbitrary constant. Okay, so ln of x square plus y square is some arbitrary constant. That means this x square plus y square is e power that arbitrary constant, which is again some constant. That's why this equation gives you x square plus y square can be written as some constant actually. Okay, so c2, let us say this c2 is arbitrary constant. Now if you see, this can be written as x square plus y square is equal to, this can be written as square root of c2 for example square. Now if you see this equation represents is of the form x square plus y square equal to a square. So they represent circle, family of circles with center at origin, correct? So this represent family of circles with center at origin, actually. Okay, so they represent some family of circles with center at origin. So when you take different values of c2, the radius changes but center remains same. Okay, so therefore these equipotential lines are actually circles with center at origin. So if you draw equipotential lines, they are something like this. Okay, okay, so all these are basically some fine. So if you see, these are the equipotential lines, phi equal to c1, phi equal to c2, phi equal to c3, phi equal to c4. Okay, so these are equipotential lines. Now these are circles. Now definitely you know one thing, first streamlines, along streamlines this psi is equal to constant, correct? So whenever psi equal to constant, look, this implies what is psi in this case, c times of tan inverse y by x is equal to some arbitrary constant. Okay, so c1 let us say, Then if I divide this c with c1, this is also the case. So tan inverse of y by x is equal to again some arbitrary constant. So this implies y is equal to tan of some arbitrary constant into x is what you have. So this is of the form y is equal to mx, correct? For different values of c2 you will get different values of this constant. So this is of the form y equal to some constant times of x. So please tell me what is this equation? This equation represents which curve? This is of the form y equal to some constant into x. So please tell me which, what is the geometry of this curve basically? If you plot this curve, what is the shape that you're going to get? Straight lines, correct? So these are family of straight lines. Family of straight lines passing through origin. Okay, so they are passing through origin. Clear? So family of straight lines passing through origin. So therefore, if you try to plot the streamlines here, the streamlines will take this shape. All these lines are passing through origin. Okay, all these lines are passing through origin. You can have different functions like this. So like this, all these are streamlines actually in this case. Okay, so straight lines from origin, yes, correct. So these all are straight lines from origin. So we know that streamlines cannot intersect, so that's why I'm not showing any intersection here. So because practically speaking, if you take some thickness, means let us suppose if the source is something like this, if the source, we have taken it as a point, but let us suppose if the source is something like this, fluid starts coming out in this direction and in this direction. So these two streamlines does not meet actually. So that's why I'm not meeting them at that point, but actually they are the radial lines which are passing through the origin. Okay, so now tell me one thing. So this is psi is equal to c1, psi is equal to c2, psi equal to c3. So these are the streamlines actually. C4, C5, you can have lot of, actually if you want you can draw some more radial lines, but I'm just restricting this. So psi is equal to C7, psi equal to C8. Okay, so that's how. Similarly you can have lot of streamlines actually. You can draw one more streamline, all this radially if you want. You can draw lot number of streamlines actually. Okay, so that's why again I'll tell you one thing. If you draw tangent at any point to this circle, for example, if you draw tangent to this point, what is the meaning of tangent? If you take small length of a circle, the tangent and that small length are almost same, correct? They are almost parallel actually. Okay, so therefore tangent and normal, this is normal perpendicular, so they are always at 90 degrees, correct? So this angle is always at 90. That's why if you see the streamlines and equipotential lines, they cut at 90 degrees. Okay, obviously because they both should intersect perpendicularly, so that's why this is how we get the things, and the flow happens in this particular direction. Okay, so the flow happens in this direction, radially in all the directions from this particular case. Okay, so is this clear? Did you all understand the concept of source actually and the mathematics that we dealt here? Okay, clear? Understood? So this is the simple concept of source. Only thing that we talked about is this c times of log z. This is the velocity potential function, I mean the complex potential function for this case. Okay, so c times of log z to the base e, that's it. Okay, so once we get this equation, then we can write this. Okay, I'm not doing this again. Okay, log z, this equation I'm not doing again because I have shown you in basics yesterday how log z can be written, so I'm directly using that. Okay, now so coming to the next situation, that family of straight lines. So therefore here if you see, we have assumed, when we are plotting this, we have assumed the source is at the origin. Okay, so that's why this function came. If source is at the location z0, for example. Okay, always the source need not be at the origin. Sometimes they can place at any point in the two-dimensional plane. Okay, means at any point in the complex plane they can place a source. So let us suppose they place the source at the point x0, y0, for example, which can be written as z0. Okay, so let us suppose they have placed the source at some point z0. Then in such case, then f of z in general is given by this constant times of ln z minus z0. Okay, so this is the generalized function, because I haven't taken z0, because if I have taken z0, then analysis would be much complicated slightly. So that's why I'm not taking that. But normally I'm just giving you this point. If the general equation for complex potential function, whenever the source is at some location z0, then this is the equation. If z0 is origin, means if x0, y0 values are 0, 0, means if the source is kept at origin, then this z0 is 0, then you'll get 3 times of ln z. Okay, which I have somewhere here, yeah, which I have written here. Okay, clear? So this is the equation. Now how to identify this constant c? That's the main important thing. Okay, so how to identify this constant c actually? So let us see here. We define one term which is called strength of a source, which is one very important thing. So strength of a source. Strength of a source. Okay, so what is strength of a source? Means how do you know how effective is the source that's available? Because look, let us suppose from the same point fluid is slowly coming out in radial directions, but from the same point some high velocity fluid is coming out, means discharge is high. So the strength of that particular source is measured in terms of the discharge provided by that source. Okay, so this is given by discharge coming out of the source, coming out of the source per unit length. Okay, so discharge coming out of the source per unit length. Okay, means practically what happens when you see in the front view, you can see only a point, correct? The fluid is coming out one point. But if you see the side view, let us suppose the fluid is coming out in all the directions from this point. Okay, of course here you can see only 2 directions. The fluid is coming out in all the directions. Okay, so this is side view of what you actually see in the front view. Okay, so actually the source is like this. Now this is the side view. Now whenever the source length is only 1 unit, means assume there is one small pipe like this from which fluid is continuously coming out in all the directions. So if the length of this pipe is 1 meter, then what is the discharge that you are getting? Okay, so that's what you are interested in. Clear? So source per unit length actually. Okay, so source per unit, I mean this discharge per unit length, and this strength of a source is unit length, and it is denoted by small m generally. It is denoted by small m. It is denoted by small m generally. Now if you see one thing, so what is the discharge that's coming out? So discharge coming out per unit length is nothing but is equal to radial velocity at any given point. Means for example, let us suppose, look, try to understand, let us suppose this is some source, and let us suppose this is some radius, for example. Okay, so this is some radius and you have kept a source at the center, for example. Okay, so at the center, now what happens? Fluid actually flows out in all the directions radially. Fluid actually flows out of this source radially in all the directions. Okay, so the fluid actually flows out in all the directions radially. The fluid moves out radially in all the directions. Okay, now whenever the length of the source is 1 unit, the velocity at this radius, for example, let us suppose if this is at a radius r and there is some radial velocity of the fluid with which the fluid is actually getting emanated. Okay, so if at every location on this circle, for example, the fluid is coming out at a velocity Vr, then can I write discharge is equal to Vr into area available for the flow. So what is the area? 2 pi r into length. So 2 pi r into length is 1 meter, because per unit length of the source. Okay, so this is the flow area and this is the velocity at this location. Okay, so u r, let us write for example UR, because we have taken UR in all our all our notations. So let us take UR is the velocity, radial velocity. Okay, this is UR. So can I write this? Discharge, whatever is coming out per unit length, is nothing but the velocity which is moving in the radial direction into the total area available for the flow. Means let us suppose there is some pipeline like this, then fluid is coming out from this pipe in all the directions. If length of this pipe is 1 unit, then how do you calculate the discharge velocity with which the fluid is coming out into this surface area which is available? Correct? So 2 pi r is the circumference multiplied by the length gives you the flow area which is available. So 2 pi r into 1, because 1 we have taken, per unit length we have considered, so that's why length is 1 unit and this is radial velocity. Clear? Are you all clear with this equation? So please type in the chat box. Are you all clear with this equation? Yes? Simple. Discharge is equal to average velocity into this flow area. That's it. Okay. So this implies, or this is equal to, discharge per unit length is taken as strength of the source m ur into 2 pi small r. So this gives you the expression ur is equal to m by 2 pi r is what you have here. Okay. So this is m by 2 pi r. This implies ur is equal to m by 2 pi divided with small r. Okay. So this is what you have. Now when ur is equal to m by 2 pi divided by r, and you have taken this ur is equal to some constant divided by small r. So this constant value which is here is nothing but m by 2 pi. Correct? So because you have taken this u small r as, you can see ur we have taken as c by r. So this c is nothing but now m by 2 pi. Okay. So c value is m by 2 pi divided by r actually. Okay. So if you replace c is equal to m by 2 pi, means if you know the strength of the source, for example, if they give you strength of the source as m, then in that case we can write this as, therefore for a source of strength m, placed at the point z0, f of z is equal to m by 2 pi times log z minus z0 to the base e. So this is the complex potential function for any source that you keep at z minus z0. Clear? Fine. Now, so this is the case basically. So m by 2 pi times log z minus z0 to the base e. So if the source is kept at origin, then this z0 is 0. So you'll have m by 2 pi log z to the base e is the complex potential function here. That's it. Okay. So streamlines and equipotential lines, all these things we have seen. Now, for example, let us suppose you have sink. Okay. Then let us suppose if you have a sink. Okay. Instead of source, let us suppose you got a sink, for example. Then let us see how you'll get this. Sink is nothing but a point to where the fluid continuously enters. The fluid continuously enters means basically, if you see, if for example if you take a sink, okay, if you take a sink like this, then to this what happens? If you take for example things like this, okay, so if this is the case, then here if you see, the fluid continuously enter this region. The fluid continuously enters the region. Okay, so the fluid continuously enters. Now if you try to analyze one thing, in this case ur is equal to and u theta. Here also fluid travels only radially, but only one thing is, instead of the fluid velocity being positive, it is negative. So you will take minus c by r. That's it. Okay. So this minus sign tells you that the fluid is coming towards the radius. It's not. It means basically it's moving in the negative direction of the radius. It's coming towards the horizon. The radius is actually decreasing. Okay. So if you see, if you try to do some mathematical analysis for this, the only thing that changes is this minus sign. Yes or no? That means if you try to do this analysis, complete analysis again, if you try to do this complete analysis by putting a minus sign here, then everything remains same except this minus here. Yes or no? That only thing that changes is this minus sign here. Minus m by 2 pi comes out. Yes? Because only see, if the only difference in this case is this minus c by r, because fluid is coming towards the radius. It is in the decreasing direction of the radius, so it is minus sign. So therefore, if you see, the complex potential function for a sink of strength m, for a sink of strength, again, strength of a sink is defined as the discharge that enters into the point per unit length of the sink. Okay, so it is basically the simple opposite of the source, where the fluid motion is actually the source actually gives you and sink actually takes, like in thermodynamics case. Okay, which supplies heat and which takes in heat. Okay, so for a sink of strength m placed at z is equal to z0, this complex potential function is minus m by 2 pi times log z0 to the base e is what you have here. Okay, so the only thing that changes is this minus sign, because you can easily understand from this analysis, the only thing that changes in the analysis between source and sink is this minus sign here. Okay, so because of that you actually get some minus sign. So minus m by 2 pi times log z minus z0 by e. Clear? Okay, because you can understand, right? Only minus sign is the difference, so that minus sign will come till the end. Okay, so the same thing. Now, and the equipotential lines, streamlines, everything remains same. The only thing is the streamlines means the flow direction actually is in the negative direction. Now I want to give you one important concept here. Doublet. Doublet. So this is one very important concept. Doublet. Okay, so what is this doublet? Let us see. A combination of source and sink of very high strengths, that are placed very close to each other. Look, there is this statement is very important, because there is some other thing which is also called the Rankine oval actually. Okay, which we will see hopefully in the next lecture. So if you see, we can call the combination as doublet only when they are placed very close to each other. Okay, let us suppose if the distance between them is very far, then you cannot call that a doublet. Okay, so the distance between them should be very small. Only in such case you can call that a doublet. Okay, so let us see what is a doublet. So here if you see, this is a combination of source and sink of high strengths placed very close to each other. So let us suppose, for example, if this is the case. Okay, now this is horizon, for example here. So this is horizon. So let us suppose you have placed one source at this point. Okay, or sink basically, and you have placed one source also somewhere here. So source, or you can interchange also, nothing happens. Normally source and sink are taken this way. So since they have to be very close, let us suppose this distance is epsilon, which is very small. This distance between these two is epsilon, and this is also epsilon. This distance is also epsilon, which is very small actually. Okay, epsilon is just positive but very small, like in limits and all we'll take this epsilon is very small, but of course it is positive. So tell me one thing, if this is z is equal to 0, this point is nothing but z is equal to epsilon, correct? And this point is z is equal to minus epsilon, because they are, of course the imaginary parts is 0 but they are complex numbers again on the same, because they two have to be very close. So I have taken in such a way that these two, source and sink, are actually very close to each other, okay, such that the distance between them is very small. 2 times of epsilon is very small actually, okay, like 0.001 meters of that order. Okay, now if you see, for source at z is equal to minus epsilon, for source at z is equal to minus epsilon, f of z is equal to m by 2 pi times log z minus z naught. So minus of minus epsilon is z plus epsilon to the base e. Okay, similarly for sink at z is equal to epsilon, this f of z is going to be minus m by 2 pi times log z minus epsilon to the base e, correct? So this is what you have. Now if you want to combine them, okay, then superposition can hold good here for the complex potential functions, because if you want to add two functions you can directly add. Okay, so therefore for the combination of source and sink, for the combination of source and sink in above case, means basically in this case when they are placed very close to each other, look, in above case. So try to understand this, f of z, the complex potential function that is required is nothing but the sum of these two functions. Okay, this is called superposition. You know, if you want to add the effect of two functions, you can directly add those two functions. So we write that as m by 2 pi log z plus epsilon to the base e, and if you add this minus m by 2 pi, because there is a minus sign here, so if you add this minus sign comes out, m by 2 pi log z minus epsilon to the base e actually. Okay, so this is what you have. Now this can be written as, the combined complex potential function can be written as m by 2 pi times of log z plus epsilon to the base e minus log z minus epsilon to the base e. Okay, so this is how we have things. Now if you simplify this slightly, I want to show you how this function actually gets reduced for this particular doublet condition. So here if you see, this implies f of z, try to look at some mathematics here, m by 2 pi into, this is of the form log a minus log b, so that can be written as log a by b. So log e to the base z plus epsilon by z minus epsilon. Okay, so we will do one thing, if you take z common from these two terms and if you cancel with this z common from these two terms, this expression can be written as m by 2 pi log of, or log of generally 1 plus epsilon by z divided by 1 minus epsilon by z to the base e, correct? So this can be written actually, yes or no? Because if you see, if you take z common here, then z of 1 plus epsilon by z, similarly if you take z here, z of 1 minus epsilon by z, so z gets cancelled. So this is what you have here in this case, yes or no? Now if you write this equation slightly, so this equation gives you m by 2 pi log 1 plus epsilon by z into 1 minus epsilon by z whole power minus 1, correct? So this is what you have to the base e. So log of, so this a by b here means, if you see this expression which is here can be written as 1 minus epsilon by z whole power minus 1. So when you add this 1 minus epsilon by z whole power minus 1, look, in binomial expansions normally you have this equation 1 minus x whole power minus 1 is equal to 1 plus x square plus x cube and so on provided this mod x is actually less than 1. Okay, means whenever x is actually less than 1, then this 1 minus x whole power minus 1 is actually equal to this expression, which you might know from the geometric expression. Sometimes geometric progression, if you see, we have this expression, for example 1 plus x, means this expression, if you see 1 plus x square and so on, this is a geometric progression with the first term 1 and the common ratio is equal to x. So in that case, sum of infinite terms of this expression is equal to a by 1 minus r, provided this common ratio has to be less than 1. Correct? Do you know this? Whenever you have some geometric progression like this, 1 plus x square plus x cube and so on, then this expression can be written as, sum of this value can be written as first term divided by 1 minus x. It means if you have a plus ar square plus ar cube and so on, then the total sum of the terms in the geometric progression is a by 1 minus r, provided this common ratio is actually less than 1. Correct? So that's how this can be used as a binomial expansion. So here if you see, therefore 1 minus epsilon by z whole power minus 1 can be written as 1 plus epsilon by z plus epsilon by z whole square plus and so on infinity. But now if you see, epsilon is very small value. Okay, so if you take z at any location, this epsilon by z value will be much smaller. Yes or no? Correct? Epsilon is actually very small length, so if you take any length on this z at some large distances, then definitely this length will keep on very small. So therefore, if you neglect these higher terms, neglecting higher order terms, okay, so if you neglect this higher order terms, then this implies your 1 minus epsilon by z whole power minus 1 is equal to 1 plus epsilon by z is what you have here. Okay, so 1 plus epsilon by z is what you have here. So if you replace this quantity in this after this mathematical understanding, then this function is of the form m by 2 pi log, this is 1 plus epsilon by z, this is also turning out to be 1 plus epsilon by z. So this gives you 1 plus epsilon by z whole square to the base e. Correct? Because this total term is turning out to be 1 plus epsilon by z. So 1 plus epsilon by z into 1 plus epsilon by z, this gives you a square. So square on the top of log can be multiplied here. So m by 2 pi into 2 times log 1 plus epsilon by z to the base e. 2 and 2 gets cancelled. So now if you see, this is equal to m by pi into, now again, log 1 plus epsilon by z. Normally if you see expansion of log 1 plus x to the base e using Taylor series, if you expand, then you will get x minus x square by 2 plus x cube by 3 minus x power 4 by 4 plus and so on infinity. Okay, so this is how we get the expansion of log 1 plus x if you expand it using Taylor series expansion. Okay, again if you neglect, but here if you see epsilon by z is very small, so if you neglect these higher order terms, so neglecting higher order terms, then here we can see log 1 plus x will be almost equal to this x again. Okay, so that if you replace here, this log 1 plus epsilon by z is almost equal to epsilon by z actually in this case. Understood how I have converted this into this expression because of this particular understanding of logarithmic function? Clear? Okay, clear? So that's how basically all this is a bit of mathematics that's involved here. Okay, you have to go a bit about this, but since you know I'm explaining you in detail here. Okay, so this is epsilon by z. Now if you see this value, this is a high value and this is very small value, so this multiplication of m into epsilon is some constant value, correct? Because we know what is the source we know what is the strength of a source and also strength of a sink. So m is known to you, epsilon is very small, so whenever this value is a bit large and if this is small, then this gives you a constant. This constant can be written as some c into pi is what it can be written, correct? So from this constant, if you this multiplication can be written as some constant value into pi, because my main aim is to eliminate the pi. So therefore if you do this constant, so let constant is equal to, let constant is equal to c times pi. Okay, so if you put that c times pi, this implies your f of z is actually equal to c by z actually here. Okay, so we have c by z is the case for the doublet. Did you get this? How I have done this? Because what happens when you add this m epsilon as c pi, pi gets cancelled, so c by z is what you have, where c is some constant. Okay, so depending upon the source and strength concepts, this c is actually some constant. Clear? So we get this expression c by z as the complex potential function for the case of a doublet actually. Clear? Fine. So that's how we have this particular case, f of z is equal to c by z. Okay, so this complex but this actually involves a bit of mathematical understanding that I have stated here. So here if you see, this complex potential function in this case for a source, means basically for a doublet, is given by f of z is equal to c by z actually here. So this is the velocity, I mean the complex potential function for a doublet. Okay, and this you can understand only after certain bit of mathematical. Look here, I didn't do any fluid mechanics. All this is slide, whatever you are seeing is only mathematical, simplifications. We have written fluid mechanics only till this particular portion. So this gives you c by z. Okay, so this is called a doublet. You can understand this in this function z power u equal to z power n, I mean this u into z power n. If you put n equal to -1, then you will get u, basically some constant, divided by z actually here. Okay, so that's how we get the doublet when n equal to -1. Okay, that's the case I thought of discussing previously, but now you will be in a better position to understand. Okay, if I say doublet, you know what is a doublet, how the complex function came, so you know this. So that's why when you put n equal to 1, so some constant divided by z is the the complex potential function. Clear? So is this clear to all of you? Actually this logarithm, all things will go and you will be left with simple expression for this case of doublet, that it is c by z. That's it. Okay, so it is c by z. Clear? So we will see the case of, I think the time is short, it's 9 o'clock already. So we have started the session late because of some issues. Okay, so so in the next session I will show you actually how we plot the streamlines in case of this this doublet, means in case of doublet how we have the streamlines, that I will show, and also we will discuss about the vertex and some superpositions like the Rankine half body and all. Clear? So these are the things that we majorly deal in the next session. Okay, so this is also one superposition. We will see superposition of this uniform flow on a on this uniform flow on this source. We will see all these things, okay, in the next session. Clear? Fine then. Okay, so we will talk about these things in the next session. So please join back at 9:30 and we will continue the discussion.